Welcome to EDU World Space.
Okay, for this problem in part A, let's start off by showing that this series converges. So for the solution here, let's go to the integral test. So here's our AN. So we look at f of x.
Here's a clean and professionally formatted presentation of the calculation shown in the image.
Defined as such.
Application of the
Now
work energy
show
theorem, WET. From the work
AN
energy
is
theorem, the
decreasing.
force F is given by F equals frac tex KE, where KE
You can either go
equals
ahead and
kinetic
show
energy, S equals stopping distance. If I'm given for object
definition of
A, FA
decreasing,
equals frac
or we can
100,000,
just show
0.10.
f is
For
decreasing.
object B, FB equals frac 225, 1500 equals 0.15 tex space N.
Now,
And
this
force
latter
ratio
case
frac
is usually
FA,
easier. In this
FB
case,
equal
go ahead
frac
and
0.10, 0.15
take a moment to
equal
use the
frac 2
quotient
null
rule.
result. A box frac FA, FB. Would you like a PDF
And when
version
you
of this
simplify, you get
explanation?
this expression, which is eventually negative. Here, if you take x larger than e, this will mean ln x is bigger than 1, so that 1 minus ln x is negative. So f is eventually negative, the derivative is negative, so that means f is decreasing. Now we go ahead and use the integral test. So let's go ahead and write this proper integral as a limit. T goes to infinity. Now, if you looked at this problem in the book, it uses CAS, which is computer algebra system, and that will come in handy right at this step because the integral is too difficult here. So using the computer algebra system, so going into any computer or calculator and just integrating this expression here, we get the following. We got a negative out here, and then ln squared x. So by that, we mean ln of x. All over x, and then from 1 to t. Now let's go ahead to the next page here because I'm running out of room. So I'll go ahead and just plug in the endpoints now on the next page. Still got our negative there, ln squared t, 2 ln t plus 2. So we plug in the t first, and then you would plug in 1. Simplify this. And now you can go ahead and take a limit. That goes to 0. ln t over t is of the form infinity over infinity. So you could use L'Hopital's rule. And this approach is the derivative of ln over the derivative of t, 1 over t, which goes to 0 as t goes to infinity. So what we just showed is this whole fraction will go to 0, so that the limit goes to 2. This means that the integral converges. And so by the integral test, that the series also has to converge. That's how we're applying the integral test, and that resolves part A. Let's go on to the next page for part B here. So for part B, we'd like to find out bound. for the error in the approximation, S is approximately Sn. So remember, S is the entire sum, whereas Sn is a partial sum. So here, recall what the error is given by. This is also known as the remainder. Which is given by the following. So recall the upper bound given in this section for the remainder when using n terms. So these are the same n here. So in our case, because we have an f in our problem here, just replace that with the definition of f that we gave on the previous pages. And now write out this proper integral like we did in part A. So using the computer algebra system, just like we did in part A to integrate, get our negative there, ln squared x, 2 ln x plus 2 all over x. And don't forget your endpoints here, t and n. Now we saw in part A that this expression here will go to 0 in the limit. We use L'Hopital's rule to show that. Now this second term here doesn't depend on t, so we'll just go ahead and simplify this. And there's our upper bound for the error. So we have Rn over here, less than or equal to, and here's our upper bound. So that resolves part B, and we'll actually use this again soon. Going on to the next page here, we want the smallest value of n such that the upper bound is less than 0.05. So solution, so we'll use part B here. This is where we had our upper bound for Rn. Now we want the smallest n such that this is less than 0.05. So just go ahead and set this guy equal to or less than 0.05. And now at this point, we could just go to any computer algebra system or set these equal to each other and see what you get for n. And since n is a natural number, we'll have to round up here. So in this case, the smallest n that we should get is 1373 after rounding up. So any of these n's will work because an is decreasing. So we just go ahead and take the minimum. This would be the smallest n that'll guarantee that this is true. Finally, going on to part D, we want to find Sn for this and in part C that we just found. So this is n equals 1373 from part D. So now we just go to the partial sum. By definition, go from your starting point all the way up to this new value. Then you just take the sum of the series. Now that's too much for us to add up by hand. So there's many, you could perhaps write up your own code. If you use Mathematica or Wolfram, you can enter this in as sum. It's a capital S. You have a bracket there, ln of n squared over n squared. And now I want to give the index, so we're summing over n. We're starting at 1, ending at 1373. Close the braces, close the bracket. And in either case, when you enter this in and round off, we get this, and that's our answer for part D, and that resolves the problem.